Assalamu alaikum wa rahmatullahi wa barakatuh. Dear students, in this session I'm discussing the issue of multicollinearity and regression analysis. In our previous sessions, if you remember, we have covered some other issues such as the issue of heteroscedasticity and also the issue of indigeneity and autocorrelation in the MAR, right? So our lecture today on multicollinearity is just part of the lecture series we have in classical linear regression model assumptions. And among those assumptions, among CLRM assumptions, one very much important assumption is that there should be no multicollinearity in the model. So what is multicollinearity regressions? You can say multicollinearity occurs when two or more independent variables in a regression model are highly linearly related, right? So this is really important. If you have a model with many independent variables and among them there are some which are correlated, then you can say we have the issue of multicollinearity in the model. Okay, technically, for instance, if you have MLRM with many independent variables, for example, you have U, which is your dependent variables, and you have many independent variables, such as beta 1, x1, or you have beta 2, x2, and you have beta 3, x3, right? And error term. So you may have many independent variables resistance, but according to classical linear regression model assumptions, these independent variables such as x1, x2, x3, and xk must not be correlated with one another. And if you found out there is any sort of relationship between these independent variables, then there is the issue of multicollinearity. Or simply you can say the assumption of no multicollinearity is just violated. So in that situation, the OL is ordinary least square method is not blue. And by the blue, we mean, dear students, the coefficients we have, the estimators such as beta 1, beta 2, and beta 3, they are not based linear and unbiased estimated, dear students, okay? Okay, once again, what do we really mean by the concept of multicollinearity? Just let me break it down once more. If you have independent variables such as x1, and this is just determined by x2, predicted by x2 or x3, or if you have x2 which is predicted by x1 or x3, or similarly if you have the x3 independent variable that is just determined or predicted by x1 and x2, in that situation you can say there is the issue of multicollinearity. Okay, in case of multicollinearity resistance, we have two situations. One is the perfect multicollinearity and another is high imperfect multicollinearity. If x1 is just perfectly determined by x2 or x2 is just perfectly determined by x1, or technically we say the correlation between x1 and x2 is just either 1 or -1, then you can say there is perfect multicollinearity in the model resistance, right? Okay, let me just show you in the graph. If you have two independent variables, one is x1, another we have x2, right? And the linear relationship among them is in such a variation that all the points we have, they are just exactly on the line, the actual points. Then you can say in this situation, the x1 and x2, they have perfect correlation resistance. Why? Because there is no any residual points that they are around the line. All of the points, they are just on the line. Then you can say there is perfect multicollinearity resistance. Or you can say the covariance, or you can say the relationship between the x1 and x2, you can say x1 and x2, that is technically 0. That is what? 1, sorry, 1. Right? If the correlation between x1 and x2 is just 1, it means there is perfect positive correlation resistance. Keep in mind, this is the situations of perfect multicollinearity, and this is really not allowed in the model. Why? Because, if there is perfect multicollinearity, so simply you can say the beta 1 and the beta 2 and the beta 3, they cannot be technically computed. The answer for them is just 0. The OLS resistance cannot compute the beta 1, beta 2, and beta 3. So very much simply, in case of perfect multicollinearity, the model is just not possible. The model is just not based in blue, right? That is just not giving you beta 1, beta 2, and beta 3. Okay, another situation, dear students, that is the high imperfect multicollinearity. This is a situation where we have the correlation among independent variables, but it's really not perfect. It is just high. Okay, let me just show you in graph. For example, we have a graph here. We have x1 independent variable and x2. And when you just check the relationship, so you can say many points, they are on the line, the actual points. But there are some points, they are just not on the line. You can say we have residual error, they are just deviated. So in this situation, since we have multicollinearity, we have correlation here among the x1 and x2, but it's not perfect. So you can say we have here high imperfect multicollinearity. We call it high because the residual points, they are just closer here, right? So many of the points, they are on the line. But in this situation, since we have the perfect multicollinearity in the model distance. Okay, another situation is if we have multicollinearity and it's really not high, there is multicollinearity such as this. For example, we have x1 and x2, and there is a relationship. There are some points they are on the line, but many points they are not on the line and they are just scattered around, right? So you can say the dispersion is just high here. So in this situation, you can say here also we have multicollinearity, but it's really not high. Right? We have imperfect multicollinearity, but it's not high. So in this situation, it's really high, and here you can say we have it's perfect, right? So this is, you should learn, dear students, that we have three situations. If you have perfect multicollinearity and high imperfect multicollinearity, it's not allowed. If there is low multicollinearity in the model, so somehow it's allowed. But what is the threshold value? How we can know whether it's really high or low? So we have, dear students, the variance inflation factor. Inshallah, I'm just explaining VIF, variance inflation factor. If the variance inflation factor is 10 or more, then it's the point of concern, dear students. It means the multicollinearity between independent variables that is just high. Okay, dear students, I'm just explaining what is VIF in other slides. Okay, now, dear students, you should learn why multicollinearity matter, right? What is the issue if we have multicollinearity in the model? Okay, we have number of effects. Number one, high standard errors. This is, dear students, really important, and we have just explained this many times. High standard error means the coefficients, the beta 1, beta 2, beta 3, when they have high standard error, then simply you can say the t-value is just not reliable distance. Why? Because the t-value depend on the standard error. When you just find out the t-statistic value for the beta 1 coefficient, right, then you should divide it by the standard error of the beta 1 code, right, head. So since the t-statistic distance is just depending on the standard error, and if the standard error is high, it's not predictable, it's uncertain, then you can see the t-value is not reliable. This is due to the issue in the multicollinearity. Another problem we have with little small changes in the data distance, the coefficients fluctuate a lot. What do we mean by coefficients? Simply the beta 1, and we have beta 2, and we have beta 3. These are coefficients. So they fluctuate a lot. There is more volatility in these coefficients if there is a little bit changes in the data distance. In that situation, the interpretation becomes unstable. When we are interpreting our coefficients, for example, we say a point increase in x is just leading to how many points increase in y, that is just not reliable. The interpretation is just not stable distance, right? Okay, the next problem, we have difficulty in isolating individual variables. If you have a model with many independent variables and they are correlated, then you cannot really find out what is the isolated individual effect of x1 or x2 on the dependent variable, because you do not know that the effect is just either coming from x1 or x2 or x3. Why? Because they are correlated among one another. So you can say reduces the explanatory clarity. When you just explain that how the x1 is just explaining the relationship in y, or x2 is just explaining relationship in y, that is just not clear. Why? Because here is the issue of multicollinearity. The independent variables, they are just correlated with one another, right? Okay, next, dear students, we are discussing how you can detect the issue of multicollinearity in the model. So we have two methods. One is correlation matrix. And the correlation, you should find out the correlation among independent variables and check if the correlation is just higher than 0.8 or lower than minus 0.8. Right? In that situation, you can say there is high multicollinearity among the variables. So you can say the positive one is indicating the perfect positive correlation, and negative one is just indicating the negative correlation. So if the value is just approaching closer to the 1, then it means there is positive correlation, but up to 0.8 is just allowed. The greater than 0.8 is just not allowed. And also less than minus 0.8 is just not allowed. Inshallah, I learn instead of first we are just running the correlation to check how many variables they are just correlated using the correlation matrix. Okay, the next method we have variance inflation factor, which is VIF. Okay, the formula is simple here. VIF is just equal to 1 divided by 1 minus r squared. Okay, this is just used in Stata software and other software to find out whether the VIF is higher or lower. So what is the concept behind VIF? Okay, if you have MLRM, dear students, and you have dependent variables y, and you have beta naught and beta 1 x1, beta 2 x2, and you have beta 3 x3, right, and error term. Now our purpose, dear students, is just to regress x1 and other independent variables. So you should type x1 here. We are assuming x1 is our dependent variables, and beta naught plus we have, okay, we are regressing x1, so you should just skip this and take the beta 2 x2, right, and then beta 3 x3, right. And next, dear students, we are regressing x2 on other independent variables. So x2, that equals, we have beta naught, and plus we have, okay, just leave this, skip this term. So take the beta 1 x1, and we have beta 3 x3. Okay, sorry. Okay, now we are regressing x3 on other independent variables in the model, right? So just take beta naught and now beta 1 x1, and plus we have beta 2 x2. Okay, I'm not using the error term here, dear students. Why? Because I'm assuming there is perfect multicollinearity between these variables. Why? Because if you assume perfect multicollinearity, this is x1 and x2, then the line, in the line, all points, they are just in the line. So we are not just assuming there is error. If there is no error, so we should not expect the error term here in this model, right? The concept should be clear. Okay, why we are just using this method? Here, I'm just regressing x1 and x2 and x3 just to check whether the x2 and x3, they are just having effect on x2 or not, right? Or whether the x1 and x3 is just having effect on x2 or not. In this situation, are x2 and x1 is just having effect on x3 or not. So here, dear students, if there is effect, then that means, dear students, there is correlation of x with other independent variables. Similarly, if you found out there is the effect, right, the x1 and x3, they are affecting x2, right, then you can say there is correlation. So the purpose, dear students, we just find out the r square value from this equation. You should find out what is the r square value, also the r square value from this equation and from this, right? So keep in mind, dear students, if the r square value from each equation or model is high, then you can say the relationship is there. If the r square value from this model is high, you can say the x1 is just correlated with other independent variables. Or if the r square value from this second equation is just high, you can say there is high multicollinearity, or you can say the x2 is just related with other independent variables. So what is the matrix of VIF, dear students? Here we are just putting the r square here in this denominator. So if the r square is high, dear students, the r square is just indicating that there is more relationship, right? So there is high multicollinearity. So if the r square is high, that is just reducing our denominator, and the smaller denominator is simply just giving us the higher VIF, dear students. The variance inflation factor is high. If the r square is less, dear students, that is the situations where there is no multicollinearity, then the r square, when it is small value, the denominator value, dear students, is just remaining high, and that is just giving us the smaller value of VIF. So simply, dear students, the threshold, or you can say this, the limit here is 10. If you found out that the VIF in any regression, for example, you found out the VIF, the variance inflation factor from this model is just 10 or more than 10, then this is a point of concern. You can say the x1, this independent variable, is correlated with other independent variables, right? So similarly, you should find out the VIF for each and every variable. So inshallah, you'll learn in Stera or in Excel, we have variable and we have the VIF. For example, you found out the x1, and the x1 value, or the VIF of the x1 is just 5. This is not a problem. And you found out the x2 value is 4. This is not a problem. If x3 value is 15, for example, then yes, you can say the x3 is kind of correlated with other variables. So you can say there is correlation, and this is a point of concern. So the average VIF, if it is less than 10, then it means generally it is acceptable. Inshallah, you'll learn how we can use the VIF in Stata to find out if there is correlation among the independent variables. Simply you can say if there is multicollinearity among the independent variables or not. So now we are using the resource Stera. Okay, resource in Stera, I'm just opening my file, my datasets. So I'm importing this from Excel spreadsheet, right? So just click on browse, and here I have a special file by the name of multicollinearity, right? This file. Okay, just click on import first row as a variable name. Okay, in this data solutions we have performance score. These are dependent variables, and I have age years, experience years, I have tenure, right, and salary. I'm just checking whether the age years, experience, and tenure, salaries, these independent variables, they are affecting the performance or not. So first you should just simply run break, and you type our dependent variable, this is performance, and then independent variables, put all of independent variables and press enter. Okay, now this is output resource. The f statistic value is less than 0.05, so you can say the model is significant. While among independent variables there are some independent, only one independent variable which is salary, that is just significant. In other independent variables they are reasons that are not significant. Okay, the purpose here is I'm not using this output unless I'm sure of what? The issue of multicollinearity. Okay, first I'm just using the correlate, right? So in the correlation, simply you can just the correlation, you can type correlate, and I'm just putting all independent variables. So we have age and experience and turnover and salary, right? And just press enter the results. Look the results. Here we have the column and rows. This is age years. So the age years with itself is just perfect correlation. This is not a problem. Okay, what is the correlation between the age years and experience? This is really high, 0.91. It's getting closer to 1. And the correlation between age years and turnover is also minus 0.14. Is not really high. Why? Because not closer to 1. In the age years and salary, again, there is some 0.8. Some have allowed it because the value of the correlation should not be greater than 0.8. But somehow you can say here is also high correlation, you can say, right? Okay, the correlation here, how they intersect in this point. Look, experience, we have 1, and experience, this is 1, and experience and tenure resistance. This is again here we do not have any correlation resistance, but experience in salary in these situations we have 0.924, and we have the issue of correlation resistance. So you can say between the experience and salary we have correlation because it's really high, and also between the age and experience we have correlation resistance. And other correlation, they are you can say negligible, right? You should neglect it. Why? Because it's not really high. Okay. Okay, now dear students, we have a special command. One way I've just told you that you just check the matrix of the correlation and check how many variables they are just correlated. And one other a special method we have for the multicollinearity, just type VIF, right, and press enter. Sorry, VIF. Okay, I've just written the capital letters. You should type the smaller, right? Okay, VIF. So now look, dear students, here the experience, the variance inflation filter for the experience is high. This is 17.30, and for the salary is 9.7, and age is 6.1. So you can say salary, age, and tenure. This is, you can say these are acceptable, right? So why? Because their values, they are less than 10, but the experience is really higher than 10. In that situation, we have a problem with the experience, right? Okay, you have learned, dear students, that we have multicollinearity, but on the average, if the average value is just less than 10, this is most of the time acceptable. But just for the conservative approach, if you just try to remove the multicollinearity from any independent variable, if you have, then we should have a way out for that, how to remove the multicollinearity from that. So here we have experience, and the multicollinearity is there. It means the experience is just correlated with other independent variables. So now in this situation, you should find out that experience is just correlated with what? With how many independent variables experience is just correlated with. So from the correlation matrix, you can just understand. Look, experience is just correlated with the salary, and also you can say the experience is correlated with the age year. So you can say the age year, right? The age factor and experience, they are correlated, or you can say the salary and the experience, they are just correlated. So from the matrix you can find out how many variables they are correlated, right, and with what. Okay, what is the solution, dear students? One very much good solutions for the multicollinearity, that you should drop the variable with multicollinearity. So you can just simply drop the variable of experience if you know. But theoretically, if it's really important for you and you do not want to drop this experience variable, then there is another method, and that is by the name of orthogonalization method, right? In the orthogonalization method, dear students, you can just remove the issue of multicollinearity. Okay, what is the orthogonalization? And the orthogonalization, dear students, we are just regressing the experience on those independent variables in which the experience have the correlation with. So I'm just running the regression. You should run reg and then take the variable which is having the multicollinearity, which is experience, right? Then this is experience, and then you should regress the experience on the variables, on all those variables with which the experience is having correlation. So they are salary and age years, simply, right? So just put the salary and we have age. Press enter. Okay, after this, dear students, you should just predict the residual. So you should type predict, and okay, the name I'm just using the experience, and this is residual, right? And comma reset. Okay, press enter, dear students. Now we have just created the variable by the name of experience residual. Okay, dear students, this is the method of orthogonalization. Now, whenever you run the regression in that situations, you should incorporate this independent variable experience residual instead of the experience, right? So you should type reg, and what is our dependent variable? Simply is a performance. And now you should put your independent variables age years, and you should skip experience, right? And then the tenure years in the salary, and instead of the experience students, you should just put the this independent variables and press enter. Now, dear students, instead of the experience independent variables, we have incorporated its residual. Why? Because this is part of the data, dear students, which have no variations or correlation with the other variables, dear students. We have just removed the correlation in this way. Why? Because in the relationship of the experience with other independent variables, we have the error term which is not correlated. So that's why I've just predicted the error term, incorporated the error term to the model, and now you can say this is the part of the variation we have. This is which is not related to the other independent variables. This is also one method of the orthogonalization. This is what is called the orthogonalization method. You can say now this experience residual, this is orthogonalized to other independent variables. It means this is now uncorrelated to the salary in the tenure years, dear students. Okay, this is a special method used for removing the multicollinearity. Okay, once again, I'm just quickly repeating the results. If you found out there is multicollinearity, one method is just to consider to drop the variable with the correlation, right? And if dropping the variable is just not okay, or you think the variable is really important for the model, then the next method is just you should just produce the orthogonal variable, or just use the method of orthogonalization uses. Hopefully the concept of the multicollinearity is clear. Assalamu alaikum wa rahmatullahi wa barakatuh.